All right, we're going to work through another example that has to do with buffers. And this one is asking us to calculate the change in pH. So what we need to do is first find the original pH and then see how the pH changes as you add these compounds to the solution. So for the initial pH, let's go ahead and do that first. We can just use the Henderson-Hasselbalch equation. It is a buffer system. So pH equals pKa. Remember to put the acid on the bottom. And the pH ends up being 4.74. So this is the pH of solution A, and it happens to be of solution B as well. And this one over here that I got, this is because we did the concentration of the base, which was, this is the, it's a soluble salt, so it's going to be this ion is the base, and then this is the acid, and notice that they're both 5, and so when you put 5 over 5, you get 1, so that's where I got that. And so this is the pH of solution A before we add the hydrogen, the hydrochloric acid to it. So we're going to now add some strong acid, and what we want to see is how the pH changes. This is a buffer solution, so our prediction is that it's not going to change very much, but we're trying to see how much it does change with a strong acid. So let's list out everything that we have in this problem. We're going to start with solution A. So in solution A, we have the weak acid, the acetic acid. It's weak, so do not break it apart. We have the sodium acetate, which is a soluble salt, so it's going to break apart. We have the strong acid, HCl, and you do break apart strong acids. We have some water, and I think that's it. So let's look and see what of these things are going to react. Now, group 1 salts or ions are not really going to do much because they're just going to break apart no matter what you stick them to. Same thing with halogens, they're almost always going to break apart. Fluorine is the exception, but most of the rest of them will pretty much break apart. And there are some exceptions. If you have silver, silver chloride is an insoluble salt, so that one would stick together. But in this case, there's nothing that the chlorine can bond to that would change the pH. So we can kind of eliminate those. The water is not going to do much compared to a strong acid and even a weak acid, so this one's not going to do much either. So we're down to 3 things left, and when you look at your things that might change the pH, what I want you to first scan for is anytime you have H plus or OH minus. If you have one of those two, you have to start with that, react it with whatever it will react with, and react it to completion. So that means you need to either react it until you have no more H plus or until you run out of the thing that H plus is reacting with. And so in this case, H plus is going to be attracted to that negative ion. And that's going to make this weak acid. Now, when you react the H plus or the OH minus to completion, it is not an ice table. We're not talking about equilibrium yet. We're just reacting it to completion. So we call it a before, change, and after table. So we have some H plus. The concentration is 0.01. We have some of the salts, and we have some of the acid, the weak acid. We're going to react it to completion, and we're going to run out of the H plus first. So let's go ahead and get that down to 0. And now we're back to having a buffer solution. We have a weak acid, and we have its conjugate base. So now we can use the Henderson-Hasselbalch equation again. You also could set up another ice problem here. So now we have 4.74 minus 0.0017. And when you do sig figs, that subtraction doesn't change your number. So notice that the pH is still the same as the original pH, which is what we predicted. So there is no change because we had lots of buffer. We had a pretty high concentration of that buffer. 5 molar is pretty high concentration. All right, now let's do solution number 2. So going back up here, solution B. So this time, notice that the concentration of the buffer went way down. So now we're going to see if this was enough buffer to keep the pH from changing. So let's go ahead and set up another BCA table. And we still have less H plus than the acetate ion. So we're going to go ahead and subtract that down to 0 again. And now we're ready for the Henderson-Hasselbalch equation. And that gives us a new pH. So now you can see that this pH is slightly different. The pH has changed because we had a low concentration of buffer. So buffers work to resist pH, but only to a point. So if you don't have enough buffer to resist the pH, then eventually the hydrogen ions will accumulate or the hydroxide ions will accumulate and you will change the pH.